Okay, greetings aspiring scientists. Welcome back again today to my lecture continuing on atomic structure, and today we're going to talk about isotopes. So let's go to my slides. So this is 1.2.2 in the IB chemistry curriculum, isotopes. So first let's define this. Isotopes are atoms of the same element. So they have the same number of protons as each other, two isotopes, but different numbers of neutrons and therefore different atomic mass. So remember, it must be true that anything that has the same number of protons, the same atomic number, must be a particular element. But we can change the number of neutrons and change an element's atomic mass, still keep it the same element, but give it a couple different properties by nature of its changed mass. So one example of this, we can look at carbon. So I think there's 3 stable carbon isotopes. I tried to generate some AI images of these nuclei, but I got a bunch of trash, so I'm just going to borrow this diagram from skepticalscience.com. Hopefully they don't mind me borrowing it, but I think it's a really good representation. So you have carbon 12, you've got carbon 13, and you've got carbon 14, and they all have slightly different numbers of neutrons, but the same number of protons. You can see in carbon 13 there's an extra neutron added in the top left. In carbon 14 there's an extra neutron then again added in the bottom right. So it gets slightly heavier and more massive each time. Alright, now we know carbon is atomic number 6, so carbon 12 has 6 neutrons. And you can count them all in there. Carbon 13 then has 7, you can count them. Carbon 14 has 8, you can count them all. So in the table on the left here, carbon 12, this is actually exactly 12.000000 going forever. It's exactly 12 atomic mass units. We will go into why that is very soon in a future lesson, but basically the atomic mass unit is defined based on carbon 12, so we set it to exactly 12. But the relative abundance of this is 98.9%. The relative abundance is how much, if you take a random sample from somewhere on Earth, how much of that will be carbon 12? The answer is 98.9%. It's quite consistent. Carbon 13, though, is about 1.1%, and carbon 14 is like 1 in 1 trillion carbon atoms, which is 1 times 10 to the minus 10%. Very uncommon, but still exists and is stable enough for us to detect it. So then the relative atomic mass, written with A subscript R, the relative atomic mass in atomic mass units of carbon is 12.0107. So you might ask, where does that come from? Well, you can kind of guess that it's a mixture of the carbon 12, carbon 13, and carbon 14 contributions to that mass. It's slightly above carbon 12, but with those little percentage contributions from carbon 13 and 14. So today we're going to talk about how that calculation works and why that relative atomic mass is the one that shows up on the periodic table. So some fundamental ideas. Relative atomic mass, as I mentioned, A subscript R. This is the number that appears on a periodic table for a particular element. What is it? It's the weight roughly compared to 1 proton. We've seen that 1 proton is about 1 atomic mass unit, 1 AMU. And so we compare all the other elements to that. So when I say that carbon is 12 AMU, that's like roughly 12 protons or 12 neutrons worth of mass. But it's relative, right? Because it's compared to 1 proton. It's not units of kilograms, for example, although you can measure atomic nuclei in kilograms. It's not very practical for what we're doing here. Then the natural abundance of an isotope. If you were to take a random sample of anywhere on Earth, or indeed most regions of the universe, I think, how much of each isotope would you find? This is expressed as a percentage of all possible isotopes of that element. So it must be true that all stable isotopes percentages added together must equal 100%. Isotope calculation then. So what we're going to do is a weighted average calculation. If you're good at math or you studied statistics a lot, you probably already know this. If not, this might be the first time though, but this is quite often used. This is often how teachers would calculate your grades from different things like a contribution from homework, tests, lab reports, those kind of things. It would be done with a very similar calculation as this. You take a value of A multiplied by the percentage of your sample, which is A, plus a value B multiplied by the percentage of your sample, which is B, and that keeps on going until you've basically included everything that's in the sample. And that will equal, for atoms, the relative atomic mass, as long as you're dealing with one element. So the letter variables are the mass of a single isotope. So from my carbon example, A would be equal to carbon 12, B might be equal to carbon 13, C might be equal to carbon 14, and then we're done. 2, the percents, the A percent, B percent, C percent, and so on, are the percentage of the natural abundance. If you take a random sample from Earth, how much of that particular isotope will there be? But the way that I've written the equation here, you must input this as a decimal number. So if you had 79%, it has to be input as 0.79, divide by 100. You might see some textbooks and people write this equation instead using actual percentages, and then they'll just divide each term by 100. You can also do that. But I prefer to write it this way, I just think it's faster. Then AR is the weighted average relative atomic mass that appears on the periodic table in atomic mass units, AMU, or just U sometimes. So let's try a simple one. We'll look at B. B on the periodic table is boron. It looks like there's 2 stable isotopes, boron 10, boron 11. And somebody measured the natural abundance of each. B10 is about 19.9% of a sample, and B11 is about 80.1% of a sample. Again, that should be consistent from every sample you take around planet Earth. So, put those into the equation that I gave. If you're looking at boron 10, that's 10 atomic mass units times its percentage as a decimal, 0.199, plus 11 AMU for boron 11 times 0.801. And you'll notice that 0.801 plus 0.199 must equal 1. And 1 is essentially a fraction that represents 100%. 1 divided by 1. Alright, so if you just put those in your calculator, you'll get 10.8 AMU, 10.8 atomic mass units. And I think you can take that as your answer. If you want to consider significant figures for this, I'm just looking at the natural abundance digits. Some people will say the boron mass has 2 significant figures, in which case I should round this to 11. But other people will say the boron mass is just counting things, right? It's counting a specific number of protons and a specific number of neutrons. And when you count things like that, they have unlimited significant figures. That's another rule. But I actually do think, because the masses are much more specific than 10 or 11, which we'll see in the following questions, it's probably better to write this as 11 AMU. Anyway, here's one with more precise measurements for the masses. Lithium has 2 naturally occurring isotopes. Lithium-6, it has a mass 6.01512, and lithium-7 has a mass 7.01600 AMU. If the weighted average atomic mass of lithium is 6.9410 AMU, then what is the relative abundance of each isotope? Okay, so now we're doing the reverse or the opposite of what the previous question had. In the previous question, someone went out and measured the relative abundance, but we are instead going to look at what the relative abundance is through a math calculation based on individual masses and the weighted average mass. So these ones get a little bit more complicated. AR equals lithium-6 mass times lithium-6 percentage relative abundance plus lithium-7 mass multiplied by lithium-7 percentage. So what I'm going to do is let the percent of lithium-6 equal an unknown number x. And then what I can write is 6.9410 AMU equals 6.01512, that's lithium-6 mass multiplied by x, plus 7.01600 AMU, that's lithium-7 mass, multiplied by 1 minus x. So where does 1 minus x come from? Well, if x is the lithium 6% as a decimal number, then from my previous slide, I've showed you that those percentages must add up to 1, or 100%. So for example, if my x is 0.25, then on the other side, that 1 minus x must be 0.75. 25% plus 75% must equal 100%. So that's what I'm doing here, and that's generally the tool that you will need to use to have only one unknown in this one algebraic equation that can be solved then. So just multiply things through, you'll get 6.9410. I'm just going to cut out the units while I'm combining things with x here. So 6.01512x plus 7.01600 minus 7.01600x. And then bring everything to whatever side you like, cancel out whatever signs you need to cancel out, but you should get this 0.07500 equals 1.00088x. And then do that final division, you will get that x must equal 0.07493, which is about 7.493%. And that's for lithium-6. On the other hand, 100% minus that number must be the lithium-7, which is 92.507%. All right. So a little bit more difficult, but try some practice questions and see if you can do that yourself. So what are isotopes' effects on the properties of an element or atom? What effect does changing the isotope type have on an element or compounds that it belongs in? There's effectively no change in chemistry. That means like the energy required or released in chemical reactions or what it tends to react with. For physical attributes, however, there is usually some small changes. You can look at regular water with hydrogen 1 versus heavy water. This has hydrogen 2 that has 1 proton, 1 neutron. And the density is slightly different, actually almost 10% different for heavy water. So 1.000 versus 1.106 for heavy water. Melting point, again, slightly different, but still significant. 0 degrees Celsius for regular water, 3.82 for heavy water. So it requires a bit more energy to separate those, interestingly. Boiling point then, similar again, only about a 1% difference, but still. Boiling point of regular water, 100, and heavy water, 101.4. I don't know why heavy water increases. That's something maybe you could look into, but I think we should just know that there's some differences in physical properties. But you can go on YouTube and watch people drinking like a cup of heavy water like Nile Red. The physical properties are generally not enough to change what we observe for these molecules or atoms. So I do want to talk a little bit about isotope enrichment. Very often we want to concentrate one particular stable isotope because of its unique properties, and probably the most obvious example is uranium, because only uranium-235, as far as I know, is really useful for nuclear reactors, and yet it's only 0.7200% roughly of any given sample of uranium that we might pull out of the ground. And that percentage is not high enough for it to behave well in a nuclear reactor. So we need to up that maybe to 2%, 3%, 5%. I think the more you up that percent, the more vigorous the reactions, the nuclear reactions become. And so when it gets really high, it becomes more like a bomb where you want all the energy released at once through its fission reactions. But that's a whole nother story. But we have to consider how to separate these isotopes. And at this level, really, I think the only way is through centrifuging. If you watched my video on classification of matter and separations, I discussed centrifuging, but basically spinning your sample really quickly at a huge amount of g-force acceleration will push the heavier things to the outside and keep the lighter things to the center of your spinning apparatus. But it only works on gases and liquids, so you also have to convert all the uranium into uranium hexafluoride gas before you can even do that. So you can imagine this is an expensive process, and then consider that the centrifuging needs to be done, I don't know, like 50 or 100 times to even get any percentage increase. So huge facilities and power needed to do that, but that's what needs to be done. That's the best technology we have these days to separate isotopes in many cases. So this is called isotope enrichment. Probably going to be a booming industry as we move into the future as well. Other important vocabulary. So I think we should know radioisotope. This is an isotope that is radioactive. So up until now, I've mostly discussed stable isotopes, those that exist for considerable amounts of time. But radioisotopes are unstable. That means they have a significant chance to decay and break apart into something else rather than what they started as. Half-life. This is the time it takes for half of a sample of a radioisotope to decay and transform into something else. Fission. This is when an atom breaks into two or more smaller particles. And then fusion, when two atoms come together to form a larger atom, fused together. So we're not really going to talk much about these beyond this slide, but still you can use this vocabulary in your explanations, and they will become a much bigger part of the physics curriculum. So let's do some practice. Calculate the weighted average, AR, of Fe. Fe is iron, using the values in the following table. So we've got 4 stable isotopes, iron 54, iron 56, iron 57, iron 58. And we've got natural abundances from 0.282 up to 91.753. So you can look at this, pause the video, try it yourself. And then I'm also going to write my solution. I'm going to go to a whiteboard. Okay. So if we want to solve this, we can use the weighted average isotope calculation. So I'll start with 54. Its percentage was 5.845, but I need to write that as a decimal number. So I'm going to divide by 100. And I'm not going to write my units here as I usually do, just because we understand this is all in atomic mass units. So that's the first one. Next we will have 56, which is the main one. That one had 91.753, so I'll divide by 100 again, 0.91. And then 57, 2.119%, so 0.02119. And then 58, 0.282%. So this is going to be a very small number. Divide that by 100 still. 0.00282. Okay, so all of these added together will equal our relative atomic mass. So I would just do all of these at once, put it into your calculator, and you should get, if you just put in those numbers, 50, 55, 0.90937 atomic mass units. And again, you can consider significant figures if you choose 2 based on the counting rationale. This is about 56. Or rather, if you assume that there are 2 significant figures, that's the answer, 56. If you use the counting rationale and say that that's unlimited significant figures, then instead you can use the relative abundance significant figures and maybe write this with 3 decimal places, 55.909. All right. So something like that should be what appears on the periodic table for iron. Let's see if there's any more practice questions. So there are 2 stable isotopes of chlorine, chlorine 35, chlorine 37. Calculate the natural abundance of each isotope given that the relative atomic mass for chlorine is 35.45 AMU. And also, suggest why several other sources report Cl35's abundance is 75.77 instead. So presumably, we are going to get an answer that's not 75.77, and we have to consider why other people might get the answer of 75.77. All right, let's go to the whiteboard again. So this one is going to be one of the reverse calculations. So instead, we start with AR. It's 35.45. That will equal chlorine 35 mass times some unknown X, relative abundance, plus 37. Chlorine 37 mass times 1 minus that unknown abundance. And you can expand those and try to simplify, bring everything with X to one side, everything without X to the other side. You should get 1.55 equals 2X, and X equals 0.775. All right. So again, with significant figures, you can say that chlorine 35 is probably about 0.78 or 78%. And chlorine 37 must be 1 minus that. So with all of those digits, it's about 0.225. And if we round it, we've already labeled chlorine 35 as 78, so these have to add up to 100. I'll say that this is 0.22. or 22%. You kind of have to make some decisions about where this rounding happens, but I want to keep this just to 2 significant figures based on the masses that we had for chlorine. So how could it be that someone got, I think, 75 and an extra 2 decimal places, whereas we can only estimate it's about 78 and 22% for each? Let's go back. So how could other sources report 75.77 instead? So you can think about that, but you should come to the conclusion that whoever got that from their calculation most likely had better or more precise instrumentation to measure the masses of each chlorine isotope. We just use rough values of 35 and 37. But the real masses of those isotopes is not going to be exactly 35 and 37. It might be 34.98, might be 37.06 or something like that. And when you use more precise measurements like that, you'll get a much better result out of these calculations. So turns out 75.77 is actually a much better calculated result for chlorine 35's natural abundance. But you'll see both types of questions, I think, on IB exams. Some of them will just give you the very rough mass number, whole number, no decimal places. But other times they'll give you 5, 6, 7 significant figures and ask you to do it that way. And they might ask you to compare the results of both those types of calculations, so it's important to think about. Okay. Moving on, practice question 3. Consider the 2 stable isotopes of gallium. Gallium is Ga, so gallium-69 and 71. Gallium-69 has a relative atomic mass, Ar, of 68.9256. So you'll notice, even though it's called gallium-69, it starts with a 68. That can happen. Well, gallium-71 has a relative atomic mass of 70.9247 atomic mass units. So again, gallium-71 starts with 70. So this is sort of the opposite of the previous question. Now we have much more significant figures. Someone measured the mass more precisely, but we're going to get better results from this calculation for sure. So if the weighted average atomic mass of gallium on the periodic table is 69.7230 AMU, calculate to 3 significant figures the relative abundance of gallium-71. Okay, so luckily we don't have to worry that much about significant figures here because it tells us exactly how much we should write in the answer. Let's go to whiteboard. Okay, so again, we're doing the reverse calculation, trying to get the relative abundance. We'll have to use the unknowns. So 69.723 equals 68.9256 times our unknown x plus 70.9247 times 1 minus x. So expand those, bring everything to one side. You should get 1.2017 equals 1.9991x. And x must equal 0.601 with 3 significant figures as our question requests. And 68.9, that refers to gallium-69, so I can say gallium-69 relative abundance is 60.1%. Multiply by 100, and gallium 71, that's what 70.9 represents. That relative abundance is 100 minus that. That's 39.9%. And we can be fairly confident with this because we've had many significant figures in the mass measurements for each isotope and for the relative atomic mass. Okay, 60.1% for gallium-69, 39.9% for gallium-71. And I think that's about as difficult as questions will get. You can't really do this reverse calculation when you have more than two types of isotopes, because you'll end up with like 100 minus x minus y minus z, and you don't have enough equations to solve that usually. All right, that brings us to the end of the whole atomic structure, first 2 units. So our guiding question here was, how do nuclei of atoms differ? And I think you should be able to say a lot of things at this point. When the number of protons, positively charged massive particles, is different, we have different elements. When the number of neutrons is different, but the number of protons is the same, we have different isotopes of the same element. When we change the number of electrons, what we're doing is just creating different ions, cations or anions, or creating neutral elements if we balance it perfectly with the number of protons in the nucleus. So that's how the nuclei of atoms differ. Hopefully you've learned some things and you can answer various questions now. Thanks for listening. Next time we will move on to electron configuration and orbitals and things like that. Hope to see you there. That's all for today. See ya.